All right, so today we're going to be talking about this. Let me adjust. Okay, that's better. All right, so today we're closing in on the end of our discussion about probability. And we want to talk about probability trees today. Probability trees are used whenever you have a sequence of probabilities where the likelihood of the outcomes depend on the one before it. So obviously these are situations where the events are not independent. So let's say that you're really interested in taking a trip at the end of the semester, and you really want to go to the National Museum of Mathematics in New York, also known as MoMath. But getting to New York and everything that's involved with that is expensive. So you set yourself a savings goal. And you say, by the end of this semester, I need to save $500 for my trip to MoMath. Now, if you do save $500, the chance of you going on your trip to New York is pretty good. But if you don't save $500, it's not as good. Now, there is a possibility for the trip to still happen if you don't make the full $500. Maybe you get pretty close. You can do some cost-cutting strategies to still make the trip work. There's also a chance that the trip may not happen, even if you do save your $500. Maybe your best friend's going with you, and they can be a little flaky. So there's a chance that they're going to back out at the last minute and you're not going to be able to go. So let's map this out. Let S be the event that you save $500. And let's let M be the event that you go to MoMath. Now, we said that the chance of you going to MoMath depends on whether or not you saved $500 or not. So those are all conditional probabilities. Our first decision about whether or not you save $500 doesn't depend on anything else. So that's a regular probability. And it has to happen first chronologically, which means it's probably going to be our first event in our tree. So let's start our tree. And we have that we saved $500 or that we did not save $500. And let's say you're a pretty reasonable saver. And so let's give the probability of you saving $500 as 0.6. So that would mean the probability that you don't save $500 would be 0.4. Now, if you do save $500, we said the probability of you going to MoMath is pretty good, but there's a chance that you won't get to go. So let's say that if you did save $500, then the chance of you going to MoMath is 0.9. And that would mean that your probability of not going would be 0.1. Now, if you don't save your $500, we said that there's a chance that you could still go to MoMath, but likelihood is that you won't. So maybe the chance of you being able to make it work here is 0.3, and over here, this is 0.7. So notice here that in each of these branches, our probabilities add up to 1. And in our first branch, these are direct probabilities. This 0.6 is the probability of S occurring. And this 0.4 is the probability of not S. However, once we hit our second branch, these become conditional probabilities. This 0.9 here is the probability of M given S, because we're on the branch that stems from S occurring. And this 0.1 here is the probability of not M given S. And this 0.3, since we're on the not S branch, this is the probability of M given not S. And this 0.7 is the probability of not M given not S. So maybe we want to ask the question that I'm sure you're all dying to know. What's the probability that you get to go to MOMAF? Right? There's multiple ways for us to get there, so let's ask what's the probability of that happening? So we can ask what's the probability of M? Right? But unlike S, where we actually have a probability of S occurring, all of our probabilities that have to do with M are conditional. So how do we answer the question of what's the probability that we get to go? Just directly. And if we look at this, we can see that the ways that we get to MOMAF are we can go to MOMAF if we make our $500 savings goal, but we can also get to MOMAF if we don't save our $500 goal. And so we can say, well, the probability of going to MOMAF is equal to the probability of going to MOMAF and making our savings goal, or going to MOMAF and not making our savings goal. But notice that these two events can't occur at the same time, right? We can't have a situation where we both make our savings goal and don't make our savings goal. So that means that this event here and this event here are mutually exclusive. And we know how to calculate the probability of OR events for mutually exclusive events. And that means that this is just the probability of M and S plus the probability of M and not S. So now we just need to be able to calculate these probabilities of these AND events, right? And if these events were independent, then we could just multiply the probability of M times the probability of S. But that's kind of the problem is, one, we don't know whether these events are independent, and two, we're trying to figure out what is the probability of M. So even if we could split them, we don't know what the probability of M is. But we have the general multiplication rule for calculating these AND events. And they involve conditional probabilities, which is great because all of our everything that we know about M is conditional. So we can rewrite each of these as the probability of S given the probability of M, or the probability of S times the probability of M given S, plus the probability of, of not S times the probability of M given not S. And these are all probabilities that we know. We know that the probability of S is 0.6. We know that the probability of M given S is 0.9. We know that the probability of not S is 0.4. And the probability of M given not S is 0.3. And the probability, or the 0.6 times 0.9 gives us 0.72. And our and 0.4 times 0.3 gives us 0.12. And so that means in total, we have a probability of 84% of making it to MOMAF. This idea of combining conditional probabilities to determine the full probability of an event happening is known as the total law of probability. There are more complicated versions of the total law of probability, but for this class, we're going to keep it rather simple. And so the formula that we are going to use is that the probability of an event A happening can be written as the probability of some event B times the probability of A given B plus the probability of not B times the probability of A given not B. So obviously this is a special case. Whenever you have these events where you have these conditional probabilities, but you don't have the full probability. But we just saw an example of where this might work, right? Where we have a sequence of decisions where one is influenced by another. And in that we may know these conditional probabilities and maybe wanting to know what is the probability of the event happening without any conditionals. So it's important to understand the total law of probability, but the total law of probability is also going to help us in our next theorem. So until then, peacing out.